So in this video we're going to talk about the fundamental theorem of calculus, which is basically the relationship between derivatives and integrals. Okay, so to give you just an introduction to this very intuitive reasoning, suppose we have a function f, right, and we want to compute its integral between a and b. Okay, so that means, sorry, that a and a point x. Okay, so that's the area. We call the area below the function f as ax, so the area is a function of the value x. Now suppose we increase this interval by a very small number x plus h, right? So we have the area at x plus h. So if you think about this in geometric terms, this is obviously very similar to, let me write this here, very similar, approximate to the area of x, right, plus, and then the area of a rectangle, right, that has width h, and the height, we could say it has height f of x, approximately, right? Now if we solve for f, we have that f is approximately equal to a of x plus h minus a of x divided by h, right? So if we take the limit when h is very small, right, we get that f is the derivative of a, right? So in other words, the area of a function f is given by a primitive of f, right? So a is the primitive, a primitive of f, right? Another way to see this is if you write the area as a function of x, right, ax, the area a at x plus h is approximately equal, using the Taylor expansion for this area, to the area at x plus h, which is the increment, times the derivative, okay, the derivative of a, right, and then plus small o of h squared, right? So when h is very small, this identity becomes true, right? Now this relationship between the area and the derivative, I mean, and the integrals, all of you have seen this before in high school, because that's what you were taught, right? But this was not obvious at all for many years. Okay, so mathematicians have been computing integrals for centuries, even millennia, right? The Greeks started with this kind of rules with the sum, the rectangles. The rules for integration were everywhere, and it wasn't until Newton in the 17th century and Leibniz that realized this rule, right? That this area, the computing the area below a curve, was the same thing as finding a proper primitive to it. Okay, and this is why calculus became such a powerful tool in the 17th century. So now the rest of the video, we're going to prove this result in a more rigorous way. Okay, so first we have to prove this thing. Okay, if f is integrable in closed AB, then the primitive the integral of f from a to x, and we call this a function of x, defines a continuous function in this interval. Okay, so suppose we have any two values x and y in this interval, right, in AB, right? And so we have f of x is the integral from a to x of this function, and f of y is the same integral from a to y of f, right? So and then we also need that if f is integral, it means it's bounded. So there's an m, which is the supremum of all the x's in this interval of f. Okay, and then, well, the absolute value is bounded, right? So m is the supremum of all these absolute values. Now we suppose that let's see, that y is greater than x, right? So we have that the limit when let's see, when y goes to x, for instance, or let's see when x goes to y. It doesn't matter, right? The limit when x goes to y of f of y minus f of x, right? And we can use the absolute value if we want. This has to be 0 in order for the function to be continuous, right? Now, how do we prove this? Well, let's just substitute the limit when x goes to y of this fy minus fx is the integral between x and y of ft dt. This is the absolute value. And now we have to use this property that says that the absolute value of an integral is smaller than the integral of the absolute value. Smaller. So this is smaller or equal than the absolute value. The limit when x goes to y of the absolute value of this integral. Okay. And now, well, this absolute value is the same as the without the absolute value, because this is going to be greater or equal than 0, so it's okay, right? And now, because the function is bounded, right, m is greater or equal than all of the values here, so we can say that this is smaller or equal than the limit when x goes to y of m times x minus y. Okay, we have seen this before. Now, the limit when x goes to y of this is going to be equal to 0. Okay, so the limit of this is smaller or equal than 0. This is 0. Okay, and so yeah, from this we have proven this result. Any integrable function, so the integral of any function is a continuous function. Okay, and the only requirement for f is that it is integrable. It doesn't need to be continuous. Okay, so an example for which the integral of f will be continuous but the function is not, for instance, is this function 0 whenever x is smaller than 1/2, 1 whenever x is greater than 1/2, so this is this function, 0, 1, and this is 1/2. Okay, so let's compute the integral between 0 and 1, for instance, or let's compute this function f, right? F is the primitive, or the integral between 0 and x of this function ft dt, right? So now that will depend on the value of x because we have a discontinuity here, right? So if x is smaller than 1/2, we have that f of x is the integral of ft dt, right? But ft dt in this interval is 0, so this is going to be 0, right? Now if x is greater or equal than 1/2, we have that f is going to be the primitive between 0 and x, right? We can separate this between the integral between 0 and 1/2 of f plus the primitive between 1/2 and f of ft dt, right? Now in this interval this is 0, in this interval this is 1. Okay, so this is equal to b minus a, in other words x minus 1/2. So this function is 0 if x is smaller than 1/2, and then we have x minus 1/2 if x is greater or equal than 1/2, right? So at 1/2 this value is 0, right? So this function is like this, and then it starts increasing. So it's a continuous function. Okay, even though the function that it's integrating, it's not continuous. Okay. Okay, so now we arrive at the fundamental theorem of calculus. Okay, this is called the first fundamental theorem. If f is continuous in a, b, then this function f, capital F, which is the integral between a and x of f, is differentiable in open a, b, and the derivative of capital F is small f. Okay, so let's see. We have f of x plus h, right, is a to x plus h f of t dt. We want to be able to get a formula for this, right? So in order to compute the derivative of that, we want to get this. We want to get f of x plus h minus f of x divided by h, right? So this becomes 1 over h times the integral between x plus h and x of f t dt. Okay, now we're supposing that h is positive. If h is negative, this is the same. You can read the proof in the lecture notes. Okay, but it's exactly the same thing. Now, because f is continuous in this interval x closed x and x plus h, it reaches its maximum value m h, okay, and mh minimum value mh, okay. And so we can say that the integral is going to be this integral between x and x plus h is going to be smaller than mh times h, which is the width of this interval, and it's going to be greater than mh times h. We know that from the previous video. Now we divide everything by 1 over h, right? And so we get this, right? So this is the expression that we're looking for. Now this is the minimum value, this is the maximum value by the intermediate value theorem, right? There's a value ch, right? Ch is between x and x plus h, right? There's a value inside this interval for which this function takes the function f takes this value, right? This is a value between the maximum and the minimum, so the function f will take this value at some point, ch, right? So this is equal to f at ch, right? Now if we take the limit when h goes to 0 of this expression, right, this is going to be equal to the derivative of f at x, right? But this is equal to the limit when x goes to, when h goes to 0 of f at ch, right? But now if you see ch is a point between x and x plus h. When h goes to 0, ch becomes x, right? So then you have the result of the theorem. The derivative of f prime is equal to small f. Okay, so now with this means that in order to find the integral of any function, we just need to find a primitive for it. Okay, which one? Well, it doesn't matter. Any primitive will do, and this is what the second theorem, fundamental theorem of calculus, says, and it's also called Barrow's rule. Okay, if f is continuous in a, b, and g is any primitive of f, then the integral of a from a to b of f is g at b minus b g at a. Okay, so the proof of this is f of x. So this integral between a and x of f t dt, according to the previous theorem, the first fundamental theorem of calculus, this is a primitive of f, right? So f prime is going to be f. So if we have any primitive g of f such that this is true, we know that this is equal to this other primitive plus a constant, right? Now let's see what's the value of f at a. We have the integral from a to a, right? But this is an integral with no width, so this is 0. And so we have that c is minus, that g at a is c, right? So now g at b, wait a minute. F, from this we say that we can derive that f of x is g of x minus c. So f at b is g at b minus c, but c is g at a, right? So the integral between a and b, which is f at b, right? This thing is equal to this. And we have this statement of the theorem, right? So, well, and before we get into that, yeah, so we will have seen maybe that what we have called primitives in the previous chapter, right? The primitive of a function like this, it's sometimes called the indefinite integral. and when you put the boundaries on it, then this is called the definite integral. Okay, but in fact the relationship between these two things, okay, which is what we call primitives, is only true after we have seen the fundamental theorem. Okay. Okay, so now the corollary of Barrow's rule is that if f is continuous in closed AB and g1 and g2 are differentiable in AB, then capital H, which is the integral between g1 of x and g2 of x of f, is also differentiable in AB, and we have this equation, right? H prime is small f at g2 times the derivative of g2 minus f evaluated at g1 times the derivative of g1. So again, if we have f is a primitive, any primitive, for instance, let's say from c to x of f, right? Then h of x is just f at g2, right, minus f at g1. Now if you compute the derivative, right, this is going to be differentiable because all of these functions are, and so the derivative of this, well, yeah, you get this derivative just by applying the chain rule. You get f prime at g2 times the derivative of g2 minus f prime at g1 times the derivative of g1, right? But this is f, small f at g, and this is small f at g1, right? Because this is the derivative, yeah, of this. Okay. One example of this is, for instance, if you have f is the integral between 0 and x cubed of the cosine of t, well, the derivative of f is going to be the derivative of this 3x squared times the cosine of x cubed. Okay, and then minus the derivative of 0, which is 0. Okay. Now with Barrow's rule, we can apply the results that we obtained in last video, so in last unit for obtaining primitives, to obtain integrals by doing integration by parts and doing change of variable. Okay, so if f and g are two differentiable functions in open AB, then the integral from a to b of f times g prime is this f of x times g of x evaluated at b minus the same expression evaluated at a, which is what it says here, and then minus the integral between a and b of f prime times g. Okay, this is just applying Barrow's rule. And then the change of variable, if g is continuous in AB and differentiable in open AB, and f is continuous in g, in the transformed, so in the mapped from g of the closed AB, then we have that the integral between g of a and g of b of f is the same as the integral between a and b of f at g times g prime. Okay, so in order to prove this, for instance, let me see this here. We can prove that on one hand we had that this integral is the integral between f at u, right, du, and this is the primitive of f at gb minus the primitive of f again at g of a, right? This is just applying Barrow's rule. And then if we have if we differentiate this expression, right, we have the derivative of f at g of x, for instance, with respect to x. What you get is f prime at g times the derivative of g prime at x, right? So let's see, and this is f at gx, right? So this is going to be the integral of this function f at gx times the derivative of gx dx, right? Is the integral of this is this primitive, f at g b minus f at g a, right? So these two expressions, this expression and this expression, are the same. Okay, so let's use all of this to compute the area of a circle of radius a, right? So we know that the equation of this circumference is y squared plus x squared equals a squared, and so from this we get, as we know, this is y is equal to plus minus the square root of a squared minus a squared. Okay, so it's clear that the area between the x-axis and this, the positive function, is going to be the same as this area, right? So the area that we're looking for is the integral between minus a of a, sorry, 2 times the integral of this function, right? So let's see, if we say, well, we can take, as we have seen before, a common factor a squared, right? So this becomes a squared 1 minus x squared over a squared, right? And we take a outside of the root, and you have 1 minus x over a squared dx, right? And now we can say, well, change the variable to, let's see how to say it. This is t is equal to x over a, right? So dt, a dt is dx, right? So this is 2a, and then let me write that one in a moment, 1 minus t squared d t 2a squared, right? And now what happens when x goes to minus a, t is minus 1, and when x goes to a, t is 1, right? And now we have to do another change of variable, because this is one of those variables that need, those integrals that need trigonometric change of variable, right? So let's write t is the sine of z, for instance, right? And so now the square root of 1 minus t squared is the cosine of z. So so dt is the cosine of z too, right? So this is 2 a squared, and then we have 1 minus t squared, the cosine, times the cosine. So we have the cosine squared of z dz, right? And now when, let's see, when the t is minus 1, the sine is minus pi over 2, and when t is 1, the sine is pi over 2. Now this primitive is easy to do once you realize that 2 times the cosine squared of z is equal to 1 plus the cosine of 2z. We've done this in unit 9. So this is a squared times the integral between minus pi over 2 and pi over 2 of 1 plus the cosine of 2z. Okay, and let's see, the primitive of this is going to be a squared times, and then we have, well, this is 1, so this is just the width of the interval, this is pi, and then we have plus the sine of 2z divided by 2 between pi halves and minus pi halves. Okay, but now this integral, you know, the sine is an odd function, and it's being integrated around symmetric interval around 0, so this is going to be 0, and so we're left with pi times a squared, which is the radius, which is the formula for the area that we all know. Okay, so let me erase this, and let's end the video with just one more integration trick. Okay, that's going to be useful in some cases. So suppose we have this integral from a to b of f of x dx, okay, any integral, and we can change the variable by doing this. X is equal to a plus b minus t. Okay, so then we change the variable. This is function of a plus b minus t, right? And then dx is minus dt, and the limits of integration is when x goes to a, right, then t has to go to b, and the other way around. So you get this, right? But this is equal to this, f of a plus b minus t dt. Right, so you see that you can, how to say this, write the original integral as an average of this. Okay, right. This and this thing is the same. So we have the integral I, or if you want my integral from a to b of f. So I is not a function of x. Sorry. Let's just write this. This is 1/2 of the integral from a to b of f plus f a plus b minus x dx. Okay. Okay, so let's use this, for instance, to compute this integral from 0 to pi over 2 dx 1 plus the square root of the tangent of x. Okay, if you don't have this trick, now this integral is a tricky one, right? This is very hard to do, but we're going to see that with this trick this is fairly easy to do. Okay, so between 0 and pi over 2, this function, let's see, at 0 the tangent is 0, right? And so this is 1 over 1, so that's bounded. Between 0 and pi over 2, the tangent is positive, so this is never going to be negative, right? So this function is bounded in the tangent will go to infinity at pi over 2, but 1 over the tangent will not. Okay, so it will be between 1 and 0, right? This is a decreasing function in this integral, right? And so let's see, let's use this formula, right? So this is 1/2 of 0, the integral between 0 and pi over 2 of dx 1 plus the square root of the tangent plus, and then we have dx 1 plus the square root of the tangent of pi over 2 minus x. Okay, now we need to know that this is going to be equal to the cotangent of x. Okay, because the sine of pi over 2 minus x is going to be the cosine, and the cosine of pi over 2 minus x is going to be the sine. Okay, and so now we have to integrate 1 over 1 plus the square root of the tangent plus 1 over 1 plus the square root of the cotangent between 0 and pi over 2, right? So let's see if we can simplify this thing. Well, we have to put everything in the same denominator, and so this is just 1 plus the square root of the cotangent plus 1 plus the square root of the tangent. Okay, then we erase this thing. And now we have, well, this is 2 plus this, and if we expand this, we have 1 plus the square root of the tangent plus the square root of the cotangent plus the square root of the tangent times the cotangent, right? But the tangent times the cotangent is 1, so the square root of 1 is just 1. So you can see that the numerator and the denominator is the same thing. This is the integral of 1. Okay, so this is the integral of 1 between 0 and pi over 2. This is pi over 2 divided by 2 pi over 4. And that's it. That's the integral, as easy as that. Okay, well, see if you can solve this integral by using the same method that we have done, and that's the end of this lesson.